Hi, my name is Marlo Daly, and I would like to talk to you today about a normal curve. Looks kind of like that. Some people call it a bell curve because when you put the mean on like that, it looks kind of like a bell. And it has some very powerful implications in the world of mathematics and in real life too. But to understand what a normal curve is, before I get into the details, we have to talk about a distribution curve. What you basically do is you look at all the different measurements. So if this is height, and this is, let's say, 4'6" and 6'9" basketball players and very short people, and I can measure how many people fall in each one of these categories. It kind of makes a curve, and that's a distribution curve. There are lots of types of distribution curves. So sometimes you find something, let's say it's called bimodal. That means there are two bumps in it. It means a lot of people are down here and a lot of people are up here as far as the measurements, and then not a lot of people are in the middle. Another kind of distribution curve is, I call a skewed curve. For example, the wealth in a country. There's a lot of people down here in the low end and just a few people that have a lot of money. This would be skewed one direction, or also called biased. But in any sense, there's all these different distribution curves that we use to measure or to represent a distribution of different measurements or occurrences. And here comes the fun part. We have to find some way of talking about them. So I'm going to draw a curve here. And it's going to be looking kind of like a normal curve. And there's a couple of things on it. The first thing we do is we talk about the average. So I represent the average by drawing a little thing that's called a mu, or a mean. Mean, right there. Doesn't mean it's angry, it just means it's the average of all the different measurements. So I can do this by adding them all together. This is a summation sign. I can take all the different measurements, I add it all together, and I divide it by the number of total measurements. 1 to n, all the different measurements. So boom, 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 boom. Give it the chicken pox. And you can see lots of little spots all over the place. And the mean is the average of all those different measurements. The second important piece to whenever you're looking at data and how to talk about it is what is known as the standard deviation. It's a little sigma, and that's how far apart all of the measurements are spread. So, for example, if I have a measurement like this, let's say this is a curve. See how those measurements are clustered tightly, let's say this is the mean, they're clustered very tightly around the mean. It's very different than a curve that maybe looks like this, where they're spread out, far apart. All the different measurements are all over the place. So the way I represent that is I say the standard deviation. And standard deviation is calculated actually by looking at how far all the measurements are from the mean. You basically measure how far that is. You take all of them together, you square them, and then you take the average of all of those. It's a very basic way of talking about that. But these two factors, the mean and the standard deviation, tell you a lot about curves. Even if it's not a normal curve, it's one of these bimodal curve, you can still have a mean, and you can still have standard deviation, which in this case it would be pretty far apart because all the measurements are really far apart. Or in my skewed data set, whoosh, where the mean might be right there, this is called the tail here, whoa, little quiggly tail. The mean and the standard deviation would be how far apart those are spread. And every curve, every distribution, you can talk about those things. And that's really important because that will lead us to information about a normal curve. So a normal curve, first thing you need to know about this normal curve is the mean, the median, and the mode are all the same. Okay, so mean is the average. The median means 50% of all the data falls on one side and 50% of all the data falls on the other side. So all the different instances, half of them are on each side. It also means it's very symmetrical. So if I were to take a mirror and fold these things over, this would look very much like this. In fact, they would be mirror images of each other. And mode is which is the most common set of data. That means it's right here. This is the most common set of data. It looks like a nice bell-shaped curve. So no matter how you want to draw it, even if it's really tight or spread out, so it's almost like, whoa. These both can be normal curves with standard deviations and a mean. Now, we dig a little bit deeper into this. There's a lot of implications. For example, when I have a normal curve, draw this, which is really fun. The standard deviation, one standard deviation away. So here's my mean, okay? If I were to put here 65%, or about that, of all the data fall within one standard deviation of mean. So if I'm measuring, let's say, height, and I know what mean is, and I know what the standard deviation is, I can say 65% of all the data will fall within that. Now, I can go out further and I can say, look, 2 standard deviations. So whoop, over here, and again on both sides, 2 standard deviations on both sides. 97% of all the data falls within 2 standard deviations. It's actually 4, but 2 standard deviations is the mean. And if I go 3 standard deviations out, 99.7% of all the data falls within 3 standard deviations. So if I'm measuring things and I want to understand, where things fit, this is very helpful. That tells me more about what a normal curve is. But I want to tell you one other thing that's really awesome about a normal curve that you don't often hear about. Remember those funky type of curves? There's, let's say, a new curve, which is uniform. Let's say the probability of getting a roll on a die, a fair die. It's a flat curve. Whether you get 1, 2, 3, 4, 5, 6, same probability of getting each of those. Or I'm going to do a crazy curve. Let's say this is a distribution curve, and if I take a sample of each of these curves, so I reach in, imagine they're all jumbled up. There's thousands and thousands of measurements that form these curves. I can take a sample, let's say blue, and pick from random a few measurements, and then say what is the average of my sample, and then I throw them back in the pot. And I take another average. What will happen is those averages, miraculously, no matter what the curve looks like, those averages fall in a normal pattern around the actual standard deviation. So I can take any curve, no matter how it's distributed, and I can grab samples, grab samples from all these different curves, and plot them. If I throw back to the samples, plot them, and it will turn out to be a normal curve. And that's how you get all that great information when people are polling, because they don't have to measure the entire population. Let's say looking fish size in the sea to get the actual what the real mean or average will be. In fact, because of those earlier things where I said, probably 2 and 3 standard deviations apart, because I know that, as long as I know how big the sample sizes are, sample sizes of n, it tells me not just what the averages are, but it tells me how close to the true average I really am. So that's what a normal distribution curve is, and that's some of the value you can gain from it. We can dig a little bit more in how to calculate that in the next time.